review. I think it's working. La la la. All right. So I wanted to return to the calculation of the area of a circle. And so like what I was trying to do, I don't know where I made the error. I made some error somewhere. But what I was trying to do was like discuss if we divided it, if we inscribed like a regular pentagon, not necessarily a pentagon, but so I'm talking about a circle of radius r, right? And I wanted to inscribe a regular n-gon, so an n-sided, polygon with equal side lengths inside the circle. And I wanted to show that we could calculate the area of the circle by taking the limit as n goes to infinity of the area of the n-gon. But I think I made a mistake in the calculation of the area of the n-gon. I'm not sure where I did it previously, so I'm just going to return to that and just work through it. So if we have n, so there'd be n triangles, right? In this, as you keep going, right? So like, for example, if I just look at the case of a square, like say fourgon, right? There's 1, 2, 3, 4 triangles, and the angle inside each would be 2 pi over n. If I'm assuming that, like if I did this picture better, you'd see that these are right angles because 2 pi over 4 is pi over 2. So if I look at a particular triangle, I'm going to focus our attention here just on this one, and I want to calculate the area of this triangle carefully. All right, so this is the hypotenuse of the right triangle inside it, right? And this angle here would be theta over 2, because, the whole angle, like here to here, is theta. All right? So that's theta over 2. And so then I can use trigonometry. So I've got like what? I've got r cosine theta over 2 for this side, right? And this distance right here would be r sine theta over 2, because it's the opposite side. Okay? And then the question is, what's the area of that triangle, right? What's the area of this triangle? Okay? The area of that triangle should be 1/2 base times height, right? Now here, the base of the triangle, so I think this is where I made the mistake. The base, you have to double this to get the whole base. That's only half the base for the triangle here, so I need twice that. 2r sine theta over 2, and then r cosine theta over 2 is the height. So simplify that, the 2's cancel, right? Although I guess I could just forego the canceling of the 2. Notice I've got 2, so this gives me r over 2. And by trigonometry, that is the sine of twice theta over 2, right? Because sine cosine times 2 is sine of 2 theta. Sine of twice the angle. Here the angle's a half. So anyway, this gives us 1/2 r sine theta. That's the area of the particular sub-triangle in the pentagon. What's the total area of the pentagon? It should be n times a, right? There are n triangles, so n times that area gives me the total area of the n-gon. So what's that? Well, that's, r over 2 times r over 2 times n sine of 2 pi over n, right? So I want to rewrite that. I can either keep the n or, well, let me just point out that you can rewrite this as, you know, pi r squared times sine of 2 pi over n divided by 2 pi over n. See, I kept the 2 downstairs, and I multiplied and divided by pi. The reason I did that is so that now I've written the expression in terms of theta, right? So we've got pi r squared times the sine of theta over theta, right? Now, to calculate the exact area of the circle, what should we do with n? Well, I mean, so obviously if we use n equals to 4, it's pretty bad, right? We're missing all this. If I was so foolish as to attempt to draw it, you know, if we could. Okay, so like roughly speaking, I'm not doing very good at making my n-gon regular here, but you know, here's a rough picture of 1, 2, 3, 4, 5, 6, 7, 8. So an inscribed octagon, right? Obviously, that's a lot better, right? Because what we're missing is just this, right? So like the error and using an 8-gon versus an n versus a 4-gon to approximate the area of a circle, we're much improved, right? So if we take the limit as n goes to infinity, that should give us the actual area, right? It's the same idea as the Riemann integral. Taking the number of approximating rectangles to infinity gives us the exact area. In the same way here, if we should let the area of the circle, so this is for the n-gon, area for the circle should be, you know, the limit as n goes to infinity of, you know, pi r squared sine theta over theta, right? But of course, I think it's easier to understand this limit if instead of using n, we use theta, right? So notice that theta is 2 pi over n, right? And that goes to 0 as n goes to infinity, right? You can even see that in the approximation, right? As the number of triangles gets larger and larger, the angle for each triangle gets smaller and smaller and smaller. It's, you know, so this is equivalent to the limit as theta goes to 0, I guess technically from the right, of pi r squared sine theta over theta. But what did we learn about the limit of sine theta over theta? Remember, we made a geometric argument like way earlier in the semester that proved that the limit as theta goes to 0 sine theta over theta is 1. Right, so this limits to 1, and we get, surprise, surprise, pi r squared. So you
So this is a proof?
Yeah, this is a proof that the area of a circle is pi r squared. Mm-hmm. Now, rigorously speaking, we can't really do that until Calculus 2, perhaps, in here, because Calculus 2 is where we learn the integral techniques to calculate the integrals of the functions that you would need to do. Like, let me give you an example. So this is a problem my brother likes to put on his Calculus 1 tests. He's like, integral from 0 to 2 of the square root of 4 minus x squared dx. So put something like this on a Calculus 1 test. Now the thing is, It takes me about a week of Calculus 2. Well, I don't know, a couple lectures in Calculus 2 once we get up and going to explain how to do this integral. The way you do this integral is with something called trigonometric substitution. It's definitely not something I should cover in here, okay? So why is this a reasonable Calculus 1 question? The question is, what area does that integral represent? See, that's the question. And if you look at this, say that's y. Well, that gives me y squared, 4 minus x squared, right? Which gives me x squared plus y squared equals to 4, which of course is 2 squared. So what are we looking at? We're looking at a circle of radius 2 centered at the origin, right? Now, that's this equation, right? Of course, when we squared that equation, we adjoined extra solutions to it. This has y greater than or equal to 0. So actually, the integrand, you know, the graph of the integrand is just this, right? That's the graph of y equals the square root of 4 minus x squared. That's the sum total of it, because beyond plus or minus 2, you're taking the square root of a negative number. It's not, you can't graph it, you know? So it's actually, the graph of the square root of 4 minus x squared is a half circle. What is this integral? What is this integral actually? It's the area of what? Not the half circle, but from 0 to 2, right? So what is this integral? This integral is the area of this piece right here, right? And what is the area of that quarter circle? I mean, the whole circle has area what? Pi r squared, which is pi times 2 squared, right? So there's 4 pi for the whole circle. The whole disk, I really should say, right? This is a common, unfortunate thing. And in Swedish, do you have a distinction between like referring to the circle versus referring to the area inside the circle? So sometimes in English, we'll say circle to mean this. And to be more careful, we should say disk to mean this. No, so you don't have a, you just say circle, like there's a Swedish word for circle?
Yeah.
What's that? Sidekin? I've said that wrong. But yeah, I mean, this is an ongoing annoyance, both in math and physics. In physics, when I'm teaching physics, I talk about a problem with a sphere. Unless I clarify, students don't know if I'm talking about just the skin of the sphere or the skin as well as the interior, you know. So sometimes I use the word ball instead of sphere to try to indicate a solid sphere. Anyway, my apologies. I will often use circle where I really should probably use disk, right? The area of a circle doesn't really make sense, honestly. It's the area of a disk that's pi r squared. And yet everyone talks about area of circle, right? So since everybody else is doing it, that makes it right, right? No, so 4 pi all the way around, right? This is a quarter, so what's this integral? It's the whole circle. Did you just say pi?
1/4 of that.
Yeah, 1/4 of that, which is just pi, right? So answer is pi. So in this particular case, because you know the area of a circle, right? You can calculate the answer. So this is kind of a trick question, but it's also a good question because it, well, the intention of the question is to remind students that, you know, the definite integral has the interpretation of signed area, right? So if you know how to calculate the signed area, Another example
How
of,
do you see that it's only like that area there? The blue one.
oh,
Why
because
is it not down the hall?
the function which we're integrating is y equals the square root of 4 minus x squared,
Yeah.
and the graph of that is not the whole circle, it's just this piece, right? So
Yeah.
what's the area under that? Well, then the question is, why is it just that? Well, the integral goes from 0 to 2. You know, if I had had the integral from like minus 2 to 2, wouldn't be 0, because that would be like this. It would be both halves. So it, yeah, 2 pi, right? And I don't have a way to integrate the top and the bottom at once, because that's not a function, right? Like the graph of the circle, the whole circle, that's not a function. It fails the vertical line test, right? You can't have both this and that outputs for a single function. Like, that's not allowed. We integrate functions, okay? So, well, I mean, otherwise the area bounded under the curve wouldn't be wouldn't be a well-defined concept. But anyway, I just thought I should do this because in this lecture we actually have derived the area of the circle, which makes this problem less, it has a more sure footing. Okay. Anyway, you got any questions about homework? Oh, okay, well. Let me see if I can find another area problem for us to work. There's always more. Let's see here. Oh, man. Rats. I lost my page in here. Ah, here it is. Here we go. So we're supposed to find the area of region R bounded by the line y equals 1/2 x. All right. And the parabola y squared equals to 8 minus x. All right, so no, that doesn't sound like the previous distracting noise in the hallway was definitely more male in nature. This is hopefully female. I don't know. Okay, so all right, so I'll try to make a picture of this thing. Another way to look at this, which I think is helpful, is x is equal to 8 minus y squared, right? So I do that because then I can see that it has an x-intercept of 8. When y equals to 0, x equals to 8, right? And it, oh, my bad, 8's over here, right? Duh. What am I doing? So x-intercept of 8, and it opens in the negative x direction, right? Because it's minus y squared. So let's see here. When x equals to 0, y is equal to plus or minus square root of 8, which is here-ish. Right, so it's something like roughly speaking, that's the x. And how about y equals x over 2? That is a line, right? Slope 1/2. So I'll draw it in orange. Roughly speaking, it's something like this, right? So what do you think? Do we want to go with vertical or horizontal? And you can see where R is, right? Where is the region R we're trying to find the area of? You see it? Yeah. It's this guy. So I think vertical is a bad choice, right? Because if you look at the vertical, it's like this here, right? But if I get over here, that's annoying because then I have to use the parabola for both the above and below, and I just don't want to do that. I mean, you could do it. It'd just be a pain. But then you have to break it up into two integrals. It's just not a good choice, right? So instead, I think we should use horizontal approximating rectangles, right? So blue lines are getting on my nerves. Let me get them out of the way. All right, so here we go. So I'm going to think of my typical infinitesimal rectangle like so. And of course, my infinitesimal rectangles, I always draw very, very big. You know, I mean, it's a guide for understanding, right? So the thickness is dy, and the width would be, the right x minus the left x, right? And you'd like to write those in terms of y. So what is the right x here? 8 minus y squared, very good. What's the left x? See there, we need to do a little bit of work, right? You got to take this right here and do algebra. X equals to 2y, right? So the line has the equation x equals to 2y. Sometimes you have to do a little algebra to solve for x, for your graph. So x, this is x sub L, so minus 2y. That's the width. So what's the dA? It is 8 minus y squared minus 2y times dy. Right, and we're doing that from this point here all the way up to this point here. What are those points? I do not know, right? We haven't figured that out yet. I know they're there. What are their values? Yeah, that should tell us the bounds. So we need to find points of intersection.
Couldn't the bound be like 8 too?
Well, that would, if we used x, then we would go to 8. If we're looking at vertical rectangles, we'd go, but even so, we'd still have to find that point of intersection, whatever that is in terms of x. But so to find points of intersection, what we do is we set the left x equal to the right x here. That's where they both match up as the point of intersection. So in this context, that's 8 minus 2y equals to 8 minus y squared. So let's rewrite that. That's y squared plus 2y minus 8 equal to 0. Does that factor? Well, 8 is 4 times 2. Oh, minus 8, though. So I need like plus 4 minus 2 or minus 4 plus 2. I think I choose the... You tell me, how should I factor that? PQ formula. But we can factor, though. So like plus 4, yeah? And then minus 2 over here, right? So 4 times minus 2 is minus 8. I get the plus 4, and I get the minus 2, which gives me 2. But yeah, you could use the quadratic formula to find that as well if you wanted to. That is true. It's just factoring is easier if you can do it. So we get y equals minus 4 and y equals 2. So in retrospect, this is for minus 4 less than or equal to y less than or equal to 2. And so let's do the integral. Integral from minus 4 to 2 of 8 minus y squared minus 2y dy. Someone's getting a talking to, I'll tell you that. Does that make sense? Yeah. So we're integrating. Now we need to integrate. So we've got 8y minus 1/3 y cubed minus y squared, evaluated from minus 4 up to 2. No symmetry in this problem, you know. There's no nice, we'll just double it from 0 to something. I mean, this is just, it's just what it is. It's just a little bit ugly, but we can do it. So 8 times 2 is 16, minus 8/3, minus 4, that's the upper bound. 8 times minus 4 is minus 32. Minus 4 cubed is minus 64, so that gives me a plus 64 over 3 because the minuses cancel. And then minus 16. So let's see here. That gives me 12. 60 minus 4 is 12. That gives me minus 48, so plus 48. Minus 8/3, minus 64/3. That gives me 72/3. I feel like that's a thing. 72 is 3 times 24. Yeah. So 72 over 3 is actually minus 24. So we've got 12 plus 48. I guess I could get my calculator from over there and simplify my life. But anyway, if I did this right, 36. I would highly encourage you to use your calculator on the test for this kind of thing, you know. Us math instructors, we're always fearful that there's somebody from the previous generation watching over us, and for shame if we use a calculator, you know. So, yeah, 36. Guess this is an answer from this book I'm using. I could look in there, huh? Yep, 36. All right, I think at this point we have done enough examples of areas bounded by curves, right? I mean, I don't know how many, I think I've done about, what, 6, 7, 8?
Yeah,
We've spent a lot of time on this. I think at this point it would be a better use of my time and your time if we started going back to earlier topics and reviewing. Yeah, so in other words, I mean, I could review test 3 stuff, but I think in the big scheme of the course, it's probably healthier for you guys if I actually start reviewing for the final at this point. Because before you know it, we'll be at the final. So let's just try to go back and pick on some things that have given people trouble in tests, yeah? So one of the things that you guys are shaky on is the logarithmic differentiation. So let's just do some more of that.
Sorry, can I have a toilet break?
Oh, yeah.
Quickly.
Go for it. No hurry.
Where is the closest one here?
Oh, that I do not know. Just start walking, you'll find it.
Yeah.
Yeah. Do, 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 do. Let's see here. Do, 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 do. Wish I had a pause button on this thing. Sadly, I do not. All right, I gotta pass the time somehow. Do, 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 do. Do, 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 do. Yeah.
Sorry for that.
No problem. So, like I said, we're going to spend some time here reviewing problems for the final.
Yeah, perfect.
And because I know, I think you were sick at one point in the semester, and I think that might have been what kind of injured you on this topic. I have a suspicion.
I think I only missed one lesson.
Right.
I think I only missed one lesson.
One lesson.
Semester. I think.
But you were distracted with sickness at one point, but I'm not sure. But anyway, let's review this. So how do you differentiate x plus 2 to the x squared e to the x? But yes, you have almost always been here. I would not argue with that. So we can't just differentiate this because it's not a power function. It's not an exponential function. It's got variables both in the base and the exponent. We really have no choice here but to use the technique of logarithmic differentiation to differentiate this. So the technique of logarithmic differentiation basically is just this. Take the logarithm of an expression, use properties of logs to simplify it, then differentiate implicitly to find your answer. So we take the log of this. We get the natural log of y equals the natural log of x plus 2 to the power x squared e to the x. All right. Now, by properties of the logarithm, we can pull down that power. We've got x squared e to the x times the natural log of x plus 2. And then at this point, we can differentiate both sides. I really can't do much more. All right. So differentiate both sides. D dx of the natural log of y equals to the derivative with respect to x of x squared e to the x natural log of x plus 2, right? So I'm going to use the triple product rule on the right-hand side here, like we talked about. The left-hand side is just 1 over y dy dx, all right? Are we okay on the left-hand side? Does that make sense?
Yeah, because that's the inner derivative to the right.
Right, exactly. So,
ydx.
exactly. So that's the derivative of the inside function. Perfect, yep. And the derivative of log is 1 over the thing. So because we're differentiating with respect to x, and we have a y here, we have to do the chain rule, and that's what happens. On the right-hand side, we get 2x e to the x log of x plus 2 plus x squared e to the x log x plus 2 plus x squared e to the x divided by x plus 2. So here I'm using the rule a b c prime is a prime b c plus a b prime c plus a b c prime, the so-called triple product rule. Derivative of the first, then multiply by the second two, and then derivative of the middle one, multiply by the first and the third, and then finally differentiate the third factor and multiply by the other two. And almost done. Now just solve for dy dx, which is what we're trying to find, right? Which was x plus 2 to the x squared e to the x times big parentheses here, 2x e to the x natural log of x plus 2. Of course, you could group some of this stuff and do some factoring. I'm not even bothering to try to simplify this, okay? There it is. So, there's two different ways I tend to ask about logarithmic differentiation on the tests, which is the one is I just say use logarithmic differentiation to calculate this derivative, all right? Sometimes I do that, right?
Where did that other term come from? X plus 2 or?
Oh, this one?
No, down on the left.
Oh, that's y. I multiply y to the other side. This is y. So multiply y to the other side. Right.
All right.
So I'm solve for dy dx. Yeah. So the one way I ask logarithmic differentiation problems is I ask without asking. In other words, I give you a derivative that you just can't do any other way, like this problem. So I don't need to make the instructions here, use logarithmic differentiation to calculate the derivative of this function, because I know full well that the only way you can do it is with logarithmic differentiation, right? There's another kind of problem, though, where I say use logarithmic differentiation, and you could do it otherwise. It would just be a pain. So like this one. So we could have something like let y equal to, oh, I don't know, the square root of x cubed plus 8 times the exponential of the sine of x squared divided by the natural log of x times x to the power 3. Right? So if you just straight differentiated this, it would be very annoying. I mean, you'd have to use the quotient rule. It'd be a real pain, right? But if we use logarithmic differentiation, it's actually not too bad. Let me show you how. So natural log of y. And I'm just going to go ahead and do it. This is 1/2 natural log of x cubed plus 8. Oh, fine. I'll write out a... I'm sorry. Let me show my work, because there are people who need to see it. Okay, so natural log of the square root of x cubed plus 8 plus the natural log of the exponential of the sine of x squared minus the natural log of x minus the natural log of x cubed. Minuses on the last two terms because we have division by those terms. We should simplify this before we differentiate, though, because like differentiating a square root is no fun, and there's no need. Like this is much simpler if we simplify it. So what we have is natural log of y 1/2 natural log of x cubed plus 8, right? And the log and the exponential are inverse functions. So this simplifies just to sine of x squared. So there was something similar on the test where it should have just simplified to 3x minus 8. I had like, you ended up like log of exponential to the e to the 3x minus 8. So like, yeah, and what's that? Yeah, that's it. Because if we have natural log of the exponential of whatever, it's just whatever. It has to be the exponential of the whole thing, right? Like you can't have like a 2 here. Excuse me, you can't have, how can I say this? It has to be that exact pattern. Like it's on the test. You should have, like the test that I gave you guys test 2. I had this was part of the calculation, right? So that's just like 3x minus 8. So it's
EXP is like
oh yeah. So this is another yeah. This is just another notation for that here. Not to be confused. Like some calculators use EE. If your calculator has like EE, this notation, that tends to be notation for like 10 to some power. So I don't even want to talk about that. It's not a notation I use. I'm just warning you. Calculators use this EE notation for like 10 to a power. But anyway, continuing, sine of x squared, this is what it is. But we can simplify the last one, right? We can pull the 3 out. I can't simplify further. That's what we're stuck with. Okay, now we differentiate. With respect to x. All right. Now, so we have 1 over y dy dx, right? And this one, so I get 3x squared divided by twice x cubed plus 8. That's the derivative of the first term. So I kept the half out just down there. 3x squared is the derivative of that. So I'm always using, you know, the chain rule, d dx of the natural log of u is du dx divided by u, right? So like I'm using that. Of course, the second term I don't do that because I've got derivative of sine of x squared, which is just what? It's just plus 2x cosine of x squared, right? So I put the 2x first because it looks nicer. If you wrote cosine of x squared times 2x, that would also be fine. And then how do I differentiate the log of the log? So this is my quote unquote u in the rule I just wrote over there, right? So what's the derivative of the natural log? It's 1 over x, right? And then I divide by u, which in this case is log of x. And then finally, the last term differentiates to just 3 over x. Now solve for dy dx. And solving for dy dx in these ones is easy. It just means you'd multiply by y, right? We've had other problems with implicit differentiation where solving for y actually was like more complicated. Here, not so much. Just multiply by y. So dy dx, what was y? Oh, y is all that. The square root of x cubed plus 8 times the exponential of the sine of x squared divided by log of x times x cubed. All right, all of that times what I have above. So 3x squared over twice x cubed plus 8 plus 2x cosine of x squared minus 1 over x log x minus 3 over x. Close big parentheses, and there it is. So is this, should we do another, or?
I think I'm fine.
You're fine? Okay,
Yeah.
cool. Is there anything else that you'd like me to review while we have some time?
Nothing I can think of like right now, but
Mm-hmm.
like maybe like at the start of the semester, some things.
The what method?
The things we did in the start of the semester.
Oh, the start of the semester, so like limits?
Yeah,
Mm,
exactly.
sure. We can take a look at some limits. Let me
So I can make a list like for things that I struggle with.
Uh-huh.
Come back next week.
Yeah, that'd be good. We'll have more time, for sure. Here, I'll look at a sample limit problem. Here's the limit as x approaches 1. Now, one of the things that's kind of interesting about limits when you come back to it is that now we know L'Hopital's rule. So it's like there's another way of doing some of these limits that wasn't available to us when we did them.
What rule is that now again?
L'Hopital's rule. I'll look at one of those in a second here. X plus 1 over x squared plus x plus 1 is the problem. But anyway, L'Hopital's rule would not be appropriate here. It doesn't apply because this is not type 0 over 0 or infinity over infinity, right? But, here's an example. This one's actually very simple, right? Because this particular one, you can do what? If you plug in 1 plus 1 over 1 squared plus 1 plus 1, you get 2 over 3, and that's it. See, it doesn't have to be complicated. If the limiting expression you're limiting happens to be defined at the limit point, you can just plug it in. Let's see here, or how about the limit as t goes to 3 of t squared minus 9 over t minus 3? I think I forgot to move the camera. My bad. There it is. Folks at home didn't miss anything too complicated there. Now here, we cannot use the approach of example 5 because if we plug in 3, we get division by 0, right?
What is easy to do?
Right, so we need to do algebra, right? So that's t plus 3 times t minus 3, right? I factor the numerator, and so we can cancel those now, right? And we've got limit as t goes to 3 of t plus 3. Which is just 3 plus 3. So the answer here is 6. Now this problem, we could have used L'Hopital's rule on. Okay? So what would that have looked like? I'm going to do a vertical step, if you don't mind, equals L'Hopital's rule, and it's type 0 over 0. So this is the limit as t goes to 3 of 2t, because that's the derivative of t squared minus 9, right? Yeah. And the derivative of t minus 3 is just 1. So we get 2 times 3, which is 6. So any way you slice it, we get 6.
What does slice mean again?
Oh, just any way you look at it. Like slicing bread, cutting things up. Look, so what would have happened if we had mindlessly and incorrectly used L'Hopital's rule on the first problem? Think about that for a second. See this? If we just said, I use L'Hopital's rule, and that's the limit as x goes to 1 of 1 over 2x plus 1, that would have getting us, listen to me, that would have gotten us 1 over 3, which is wrong. See, we cannot apply L'Hopital's rule unless we have 0 over 0 or infinity over infinity as the limit type. Those are the terms and conditions for applying L'Hopital's rule. And if you apply L'Hopital's rule when it's not the case, it will mislead you. Yeah. Let's see here. How about limit as x goes to 0 of x minus sine x over x cubed. No! Oh, man. Oh, look at that. That's so sad. Here, little boy. I'll make it, there, I got that much out of it. So sad. Now here, we can use L'Hopital's rule, right? Because this goes to 0 and that goes to 0, right? So what do you got? You got limit as x goes to 0 of 1 minus cosine of x, right? Over 3x squared. All right, so then what is cosine of 0?
1 maybe.
It's 1. 1 minus 1, 0, right? Oh, look, it's still 0 over 0. It's still type 0 over 0, right?
Yeah.
So I can apply L'Hopital's rule again. And what do I get? I get sine of x over 6x. Oh no, it's still type 0 over 0.
Yeah.
Right? So we can apply L'Hopital's rule again. Okay? Hopefully this time we'll be done. What do we got? Derivative of sine is cosine. Derivative of 6x is 6. So we get cosine of 0 over 6, also known as 1/6. So the answer here is 1/6. So I think that right there is a pretty good example. I like that example a lot, actually. So, my final example for today in terms of review, I want to review a closed interval test problem, because on the last test, everybody was struggling with how to approach that problem. And maybe I just didn't spend enough time in class on it. I don't know. But these problems are easier than graphing, just graphing a function. So here's a problem, consider, I don't know, f of x equal to, e to the x squared on, let's say, minus, we'll say, minus 1 to 3, okay? The question then is to find the maximum and minimum values of that function on that closed interval. See, it's a closed interval, right? So when you're faced with the question of maximize or minimize a function on the closed interval, you want to use the closed interval test. So closed interval test says we have to evaluate the function at the endpoints and also